Alright, this is celestial navigation on a flat earth, the noon sun sighting, referring to when the sun is locally highest in the sky, and you could get a lot of information from that. Now, if you're familiar with the way the sun works, you can get a lot of information with the noon sun sighting, even without an almanac or an ephemeris. Um, During equinox, the sun is 0 degrees latitude, and during the summer solstice, it's 23.4 degrees. So here I showed how the longitudes are broke down on a globe. There's 36 lines, when on a flat earth it's 24 lines, showing that it's an hour for every zone. And I think they changed it on purpose so we wouldn't recognize that the heavens are literally a clock. Anyway, what we're going to do is take a 1 meter stick and put it as upright as possible. And when we get close to noon, we're going to start marking the shadow length with a time next to it. And when the shadow is at its absolute smallest, that's going to tell us a couple things. For starters, it'll give us true north, and also it will help us get our longitude. And if we use the cosine of the shadow length, we can calculate the angle to the sun without a sextant. Now, as I've said before, the Gleason's map is a longitude and time calculator, and I figured out what the arms were for. The bottom arm is for longitude, and it is sitting on the prime meridian or 0 longitude. The longitude running down, lining up with Greenwich, UK. The hand to the left is for time. And after looking into this, I'm just about certain this map was literally made for time and celestial navigation. So the bottom hand represents 12 o'clock, and then the other hand is 5 time zones over, so UTC minus 5. But with daylight savings time, it's UTC minus 4. You got to pay attention to that. It can get confusing. So I record the date, April 4th, 2023. I record the time of the smallest shadow length, which is 1:04 p.m. I record the length of the smallest shadow, which is 0.68 meters. And I record the sun's elevation angle from the horizon. We'll call it 55 degrees. Now with my flat earth map, I grab the ephemeris and I can get my latitude, longitude. So I look in the ephemeris for the sun location on April 4th, 2023. And I can get the sun's GHA, which is Greenwich hour angle, and the declination. And it's 13:04. I'm UTC minus 4, so I add 4 hours, and that is 1700. And I get a GHA of 74 degrees 15 minutes and a declination of 5 degrees 46 minutes. Next, I go to increments to narrow down my longitude, and because it's 1:04, so the 4 minutes, so I dial it in and I check what I add to the GHA, and it's a little over 1 degree. I'll get into the specifics, but I'm just giving the basics here. I'll get into specifics in another video, but so I add 1 degree to the GHA, so that gives me 70, we'll call it 75 degrees longitude. That is my longitude. So technically it's the sun's Greenwich hour angle or longitude, but since I'm lined up with the sun, obviously it's also my longitude. And remember, this GHA, it seems confusing. All it is the angle of the circle from 0 degrees at Greenwich, UK, around 360 degrees, around in a circle, like a clock. So GHA is longitude, and declination helps you get latitude. So if the sun's GHA were 0, it would be sitting right on the 0 degree line, or that bottom hand, or the prime meridian. Now for the latitude, the declination was 5 degrees and change. We'll say 5 degrees. So we take our elevation angle of 55 degrees, we subtract that from 90, and we get 35 degrees plus the 5 degree angle. Gives us 40 degrees. So our latitude is 40 degrees north. If it's negative, then it's south. But the ephemeris said 5 degrees, which means it's 5 degrees north of the equator. If it had been equinox, it would have said 0 degrees and we wouldn't have added nothing. So think about that. If we'd have measured a 55-degree elevation angle on equinox, then that would mean we're at 35 degrees latitude. We wouldn't have added the 5 degrees. So our latitude's 40 degrees. Our longitude is 75 degrees. Now them little lines, there's the circle around the 40 degrees latitude, and that's our location. That's our exact latitude and our exact longitude. And we see where that puts us, and that puts us right there in Philadelphia. So the GHA is the circle from 0 to 360 degrees, starting at the prime meridian. And the declination, so think about this, the declination is always going to be between negative 23.4 and positive 23.4. It goes back and forth. So the ephemeris gives us the GHA and the declination of whatever body you're looking for. And remember, the GHA starts at the prime meridian, or Greenwich meridian, and it goes from 0 to 360, and the declination is the angle away from the equator. So for the sun, it's always going to be between negative 23.4 and positive 23.4. Now the stars go all the way almost to 90, so the angle away from the equator, the declination for Polaris is like 89.9 something. In the south, for the stars, it gives you negative for the angle away from the equator, but it only goes down to negative 63, I believe, for Acrux. So that's almost a whole third of the southern hemisphere where there's no stars to navigate by. So this could have went in my previous video where things we would expect if the southern hemisphere were larger than the northern hemisphere, and that would be we would expect no navigational stars in the far south, and that's exactly what we get. Now, like I said, this map is a longitude and time calculator, so here's how the time works. So in this case, it's 5 hours, or UTC minus 5 from Greenwich, but you can compare it to anywhere else in the world. There's a clip on there, and you clip it from where you're at to where you want to compare it to, and then it spins around like a clock from 12 on back around, all the way around back to 12. And it was patented, and like I said, I think this is what was used for celestial navigation. I don't see how they could have a globe out there and try and do anything with it on the water, like to figure Capricorn and angles to all that. Now they have Google Maps or Google Earth, they could show you, but they didn't have that. So they would have relied on something like this. I'm a firm believer in the fact that the globe was made from an AE map. So here's a glance of my next video in this series, and it's going to be covering the surface area of a flat Earth compared to a globe. I think it's closer than most people think, although there are some discrepancies. And then I will be covering celestial navigation on a flat Earth using the stars and the distances, and I think a lot of people are looking forward to that. So thank you very much.